We're going to be studying today, continuing our discussion of linear programming. So we introduced this last time. It's a general class of problems that involve a linear objective and linear inequality constraints. And we discussed the fact that any such linear program can be put into a canonical form where we ask to maximize our linear objective function subject to the constraint that ax be less than or equal to b. And this is a matrix representation of the constraints. And on the right-hand side, we get a vector, and this is shorthand for saying that aix is less than or equal to bi for all I rows of A. Yes? C here is referred to as the objective of this linear program. Now, I also introduced you to the standard form, which is written out as a minimization problem. With equality constraints in the matrix, along with non-negativity constraints on the variables. And there was one really important idea for transforming into standard form, which was the introduction of these slack variables. Which are variables that exist simply to tell you how much slack you have, the gap between the current value of a constraint and its bound. Okay, so we showed that every linear program can be transformed into canonical form or into standard form. And today we're going to start talking about solving them. But as I sketched out last time, we're not going to do that all at once. First, we're going to start talking about the structure of the solution and checking if there exists a solution. And also checking, or sorry, let me not say checking. Verifying that there's no solution. Right? If you recall, last time we said that a linear program is infeasible if there is no solution that satisfies all the constraints. Doesn't matter what the value of the objective is for these infeasible solutions. Then we're going to ask about verifying the optimality of a solution. And only then are we going to talk about finding a solution. Okay. And actually, we're not even going to start with linear programming. We're going to start by asking all of these questions about systems of linear equalities instead of linear inequalities. Because in doing so, we're going to prove a number of lemmas that we need for the general problem of linear programming, and we'll also gain insight in how we attack these things in this simpler case. So suppose that we're given a linear system of the form ax equals b. And let's talk about the structure of a solution, and in particular, when does one exist? Okay, and let's start by asking the baby case of a square matrix. Okay. So for starters, is there a way to show me that I can easily verify that a solution exists to this problem?
You check
if I come in and ask you if there's a solution to this problem, how would you convince me that there is?
You check if A is invertible.
Okay, so I can certainly check whether A is invertible since it's square. Now, if it is invertible, that tells me there is a solution, right? I'll record that in the notes in a minute. If it's not invertible, does it tell me anything?
No.
Okay. Also, to tell me to invert the matrix is giving me too much work. So is there an easier way to convince me that there's a solution?
Row reduction.
But then I have to check that you're doing the row reduction properly.
I can just
Right.
give you a solution.
Right. Show me X. Right. And now I can verify with some elementary, with some basic math. Right. No complexity in verifying the solution. If we posit the matrix to be an n by n matrix, then this verification is going to take me order n time, right? But wait a minute, can you show me X? In particular, can you write X down? So now I have to be a little worried, right? Maybe there's a solution, but it's irrational, right? And so you can't actually write down that solution for me to read it and check it. So let me flag that for a moment. But I will state the following equivalent statements, which you probably know from your linear algebra class. A is invertible. A transpose is invertible. The determinant of A is not 0. A has linearly independent rows. Or equivalently, A has linearly independent columns. And if any or all of those are true, then AX equals B has a unique solution for any B, right? But actually, this is also equivalent to AX equal B having a unique solution for some B. As long as there is some B where AX equals B has a unique solution, then it's also true for every other B. Okay.
Excuse me, can I ask a question?
Yes.
Why is it the verification is O of n? Shouldn't it be O of n squared?
Oh yes, thank you. N squared. I do actually have to check the constraints. Okay. Whoops. All right. But let's come back to this question of writing it down. So if you think about it, what this is, you know, we've already, in the context of Maxflow, talked about the sort of complexity of writing down numbers, right? So we know that an integer n uses log n bits to write down the value of an integer. And similarly, we can write down a rational number, p over q, using log p plus log q bits, right? So I'm going to refer to this as the size of the number n. This is the size of the rational p over q, right? So what can we say generally about the size in bits of a product? How can we express that in terms of the sizes of the individual numbers?
Just a sum.
Yes, right? The number of bits is basically the log of the number. So taking a product adds the logs. If we now consider an n vector, a vector of n numbers, its size is n times the size of the numbers that are in that vector, right? Or if we want to be more precise, it's the sum of the size of the numbers in the vector, plus log n, of course, to capture, to indicate the size of the vector itself, most likely, okay? And similarly, a matrix, right? Is going to have size equal to the sum of the entries in the same way, right? Or mn times the size of a single entry, right? Now, what can we say of the size? That's interesting. About the size of a matrix product. Right, what's the size of A times B, where A and B are matrices? Well, I won't dwell on it, but in much the same way, you can argue that the size of a matrix product is at most the sum of the sizes of the matrices. Okay. So this gives us a way of talking about the sizes of inputs. And our goal as theoreticians is going to be to have algorithms that are polynomial in the input size when we represent the inputs using these numbers and matrices, okay? So the worry is if I give you a matrix with numbers of certain size, that the value x that solves that matrix may involve numbers that have many, many bits. And so just writing down the solution may take space and time that is not polynomial in the size of the input matrix and constraints A and B. Okay. So the first thing we have to do is do away with that worry. And the crux of that claim is that if A is an n by n matrix, actually, that's writing more than I need to. The claim is that the determinant of any matrix A, it has size polynomial in the size of A. Okay. And we'll flesh this out afterwards, but if you can write down the determinant, then you can write down the inverse, and you can multiply the inverse by something, and that all gives you vectors whose size is polynomial in the input size. And so we're going to be fine. But let's prove it. So we have this n by n matrix A. Okay. And what we'd like to do is understand the size of the number that can come out of that determinant. Okay. So I'm going to use a particular formula for the determinant, which many of you have probably seen, but some not. It's a sum over all permutations from the first n numbers to the first n numbers of the sign of that permutation. Hello. Wow. Sorry, new tools, always very confusing. Okay, it's decided to stop registering. Hold on a minute. It's charged. Hello, pencil. Well, this experiment might be coming to an early end.
You can try switching to like the eraser, then try switching back and see if it starts registering after that.
It's not even letting me switch to the eraser. It's not registering the pencil at all.
You can do it with your finger though, right?
Oh, there's an idea.
Sometimes to repair it helps to like take the end off the pencil and like put it in the charger port.
Oh, this is a new pencil. It doesn't have a charger port. This charges, you just snap it on magnetically and it charges wirelessly. But it's noticing the pencil. Sorry, I'm going to take 2 minutes to figure this out, and then we will abandon this experiment for. Why would it It's charged, and that almost certainly means that it's paired. Getting nothing.
Sorry, maybe the tip is not adjusted, the tip of the pencil. That happened to me once.
What do you mean by adjusted, though?
Like,
there we go. It's back. I think the tip unscrewed, actually. Okay, so we take the sum over all permutations of the sign of that permutation times the product over all of the entries of a particular row and column, right? So have people seen this formula before? Essentially, what it's saying is that you take your matrix, and to get a single term of this product, you kind of pluck one entry out of each row and column, and you multiply them all together. Okay, and that gives you one term. You then multiply it by the sign of the permutation, which is plus or minus 1, depending on whether you've done an even or odd number of swaps to create that permutation, and then you sum that over all of the terms. Okay, so this is not a formula that you would want to compute in practice, right? It has n factorial terms in it, so it's not polynomial time to compute, but it is a very nice formula for analytic purposes. So since we can write the determinant this way, what does this tell us about the size of the numbers? Well, what's the size of one of these products?
N times the size of an entry.
Exactly. So one of these products is going to have n of our numbers in it. So its size is n times the size of an entry. Okay. Now I just said we add a tremendous number of these, right? N factorial terms. What does that do to the size of the output?
It adds log of n factorial to it.
Exactly. So here, we're basically looking at a number whose value is n factorial because there are n terms, or n factorial terms, times, well, what is essentially, there's some gesture that turns on the eraser and I haven't figured it out yet. A size of an entry to the nth power, right? That's the size of the number that we're going to deal with. But, you know, we're counting bits, so we take the log of everything. So the size is the log of n factorial. Somebody who's typing is not on mute. So the size is the log of n factorial plus n times the size of an entry, which is equal to, what's the log of n factorial?
N log n.
That's Stirling's approximation. We have Stirling's approximation to give us that. It's about order n log n plus n times the size of an entry, right? So this is polynomial. This quantity is polynomial in the size of the individual entries and also in n. So it is polynomial in the input size. Correct? No questions? All right, so now, as a corollary, we know that the inverse of a matrix can be written as 1 over the determinant times the cofactor matrix. Right? In particular, the particular entries of this matrix have the form determinant of most of the matrix with the I column and j row removed divided by the determinant of the whole matrix, right? And what is the size of this? Well, we've already argued that this has polynomial size and this has polynomial size. And that means that we can, we know that the entire rational number has polynomial size, right? So that tells us that the solution to AX equals B, right? That is just X equals A inverse B, right? And we've already said that this has polynomial entries. And well, this is part of the input. So of course it's polynomial in size. So that tells us that the size of X is polynomial in the input. So we can in fact write down the solution. Okay, and once we write it down, anybody can check it in order to verify that it is in fact a solution. And that involves a polynomial number of operations involving numbers whose size is polynomial in the input. Okay. Now, I do want to emphasize, I said size is polynomial in the input, but remember that that polynomial includes an n log n term. So you could start with a matrix whose entries are all 0 and 1 and end up needing to use n bits to write down, or n log n bits to write down the value of the determinant of that matrix. Okay, and so that is a huge number, but it's only a polynomial number of bits. Okay, so that's good.
For each entry of the
Exactly, and then you might need that, right? If you're actually writing out the determinant, writing out the inverse, right? You're going to have n squared of those gigantic numbers. Right, and similar, x itself may consist of, it's a vector, but it may consist of n of those gigantic numbers. Okay, but gigantic, but still polynomial. Okay. All right. Now we know how to write down and check. How do we actually find a solution? What did you learn in your linear algebra classes?
Inverting a matrix is probably a bad idea, but you can do that. Alternatively, Gaussian elimination is a good option.
So we have Gaussian elimination, right? Or matrix inversion. Okay. And if you think about how these are performed, these do involve a polynomial number of operations. Okay. And you can show that they all involve numbers that are small integer multiples of the determinant. Okay, so all of the numbers that you run into while you're performing Gaussian elimination will be numbers of polynomial size. Okay, so this does have to be proven separately, but you don't get any intermediate numbers that are crazy large. They're all polynomial size. You do a polynomial number of operations on them, and therefore you end up with a polynomial time algorithm doing Gaussian elimination. Okay. All right, so let's generalize. What if A is not square? Okay. Now what do we do in order to find an answer? Well, the assertion that A equals B is simply saying that the columns of A span B. Right? So in order to look for an answer, this will be true if and only if a maximal linearly independent subset of these columns span B, right? So find those, and now you can extend these linearly independent columns to a basis by adding some more vectors, okay, with some additional independent columns. And since you created a basis, our statement above says that there is a unique solution let's call this matrix A prime, to the problem that A prime X is equal to B, but now A prime is a square matrix. So the previous analysis applies. Right? And that gives us a unique X. And so this is a way to make the columns of A prime sum up to B. How do we know if there's a solution to AX equals B? Well, if there is a solution, it has to be this one. And so X has to zero out the added basis columns. Right? When I add these basis columns to A to form A prime, I'm creating more opportunity, more degrees of freedom for choosing X. But even though I've added all of these degrees of freedom, the previous argument says there's only a unique solution. So that also has to be the unique solution that works with the original subset of columns if they're going to be able to span B at all. All right. So this really rapidly reduces to the other case. And check and find, we can find and check an answer here in polynomial time. Okay. But now let me invert the question. Okay. Before, I was asking about an easy way for you to prove to me that there's a solution to AX equals B, right? Which I'll call a witness.
Excuse me. Yeah.
For solvability. Yes, a question?
So it's not clear, I guess, why if you add some columns to A, then their values remains polynomial in the input size.
Well, I'm just going to add, I can choose columns from the usual basis, right? 0 everywhere except for 1 in a few places.
Okay. But I mean, they should be orthogonal to the columns of A.
Well, sorry, I shouldn't have said basis. Let's just extend it to no, it's a basis, right? I didn't say it's an orthogonal basis.
Oh, I see.
Okay.
But I mean, okay. How do you choose that? Like,
well, as I said, I mean, this actually can be done by solving other systems of linear inequalities, but I don't want to dwell on it too much because this is your basic linear algebra. Where I'm going now is to something that you may not have seen, because this is not the kind of question that you necessarily ask. So we gave this way of solving or of proving that there is a solution, right? But can you give me a fast proof that there is no solution? Right, so we have an algorithm for constructing a solution, but if I want to convince somebody that there's no solution, I can't just tell them my algorithm doesn't work because they'll assume that I implemented it wrong, right? So it's much more challenging to come up with a different way to prove that there's no solution with a proof that's easy to verify. Okay. So we're going to go back to the idea that if there is a solution, that means that the columns of A span this vector B. So we need to prove that this is not true, that the columns of A don't span the vector B. Okay. That is, we need to prove that B is not an element of the set of points AX over all possible X in my vector space. Yes? Now this, of course, is a subspace, right? So what we're trying to do is prove that the vector B is not in the subspace spanned by the columns of A. So let's look at the 2D case of that. Okay. So in the 2D case, the subspace AX is just a line through the origin. Okay. I have a single column A, and the set of points that are spanned by A is simply a line through the origin. Now I'm considering some point B, and I want to prove that B is not spanned by A. Okay, put it over here. So what does it mean that B is not spanned by A? Well, it means, I'm really starting to like my whiteboard. It means that B can be broken out into a component that is in the subspace and another component that is not in the subspace, right? And because B is not in the subspace, it tells us that the component that is perpendicular to the subspace is not 0. Okay. So let's call this perpendicular portion Y. Okay. And what this tells us is that Y is part of B. So Y dot B is not 0. However, Y is perpendicular to my vector A defining the subspace. So YA is equal to 0. Yes?
Yeah.
So this is a proof of no solution, right? You just give this vector Y. And now all I have to do in order to verify that there's no solution is compute YB and compute YA. Right? So very simple computation to prove that there's no solution. Any questions about that? Well, let me ask. Can we construct the proof? That is, can we find this vector Y?
Well, do we know like the component of B along A? Isn't that just like A dot product of B or something?
Good. So we can do a bunch of math to sort of essentially subtract out the projection of B onto A, right? One sort of elegant way to write that down is to notice that if YB is not equal to 0, there is some scaled version of Y that achieves YB equal 1, right? And that means that instead of having this difficult to work with not equal to 0 constraint, I can just say I want YB equal to 1 and YA equal to 0. Obviously, scaling Y is not going to change the fact that YA is equal to 0. And that can be written down in matrix form, where I put A on the top and B underneath it. I guess I'll have to transpose B here. No, I don't. Sorry, what am I saying? And so this is going to have to be equal to 0 and 1. Yes?
Yeah.
So this is just another linear equality system, right? We already know how to solve linear systems. And notice this also tells us that the size of this witness y is polynomial in A and B. Yes?
Yeah.
So this is actually kind of interesting. There's a kind of duality going on here, where we started with a linear system, and we know how to solve that linear system. And if there is no solution to that linear system, then here is a different linear system. And the solution of this linear system proves that there's no solution of the other linear system. And if you think about it, this goes both ways. If I can solve the first linear system, then I cannot solve this linear system because this linear system provides a proof that I can't solve the first one. Yes?
Huh. Neat.
Yeah, this is pretty cool. And we'll be taking this idea much farther. Okay, so this kind of ends the story of linear equalities. Okay, in polytime, we can find a solution. Easy to check. Right? And in polytime, we can determine that the solution is not possible. And give a proof that is easy to check that there is no solution. Okay. So that's the end of the story for linear systems. Any questions about that? All right. So now we're going to move on to inequalities. Okay. And that is going to, oh, sorry, I should have made clear. I didn't state this explicitly, but I demonstrated this with a 2D case. Okay. But this actually applies generally, okay, to any vertex. And I neglected to prove that to you. So before we go on to inequalities, let me give you the general proof. Okay. So the claim is that AX equals B has no solution if, and this is actually turns out to be an if and only if, but we need, that sort of follows out naturally from the proof. There exists a Y such that YA equals 0, but YB is not equal to 0. And the proof is actually quite straightforward. Okay. Suppose that you do have a solution, AX equals B. Okay. Then what can I say about YB? Well, I just said that AX equals B. So I can write YB as YAX. Right? But now we're considering, right? We're saying, I'm proving the the converse, right? I'm saying if AX equals B does have a solution, right? I'm going to show that there's no Y, which works, right? So if AX equals B, then that tells me that YB, which is, it can be written as YAX, but then YA equals 0 will imply that YB is equal to Y times AX, which of course can be written as taking the YA part first and multiplying that by X. And that's going to be equal to 0. So now we have an if and only if, right? So above, over here, I showed you that if there is no solution, then the perpendicular portion of B, the part that's not spanned by the vectors of A, becomes the Y that satisfies the requirement. On the other hand, if there is a solution, then there is no way for me to give the infeasibility witness, because anything that satisfies Y equals 0 is also going to satisfy YB equals 0. Okay, so this is the if, and this is the only if portion of this general theorem. Okay, so now we can go on to inequalities. Okay. However, this lecture has been a little math heavy, and so I want to take a couple minutes break to just let you stretch your legs, because I'm afraid the rest of the lecture is going to be kind of math heavy too. There are no real algorithms in this lecture. It's the only one. It's the only lecture in this course which doesn't have an algorithm in it. So why don't we take a 2-minute break, and then we'll come back and do some geometry of inequalities. But are there any final questions about linear systems before we do that? Nope. Okay. Then we'll resume in 2 minutes. All right, can people hear me now?
Yep.
Okay, great. Sorry, I'm trying something a little different here. All right, so picking up from where we left off, we're now going to be talking about the geometry of systems of linear inequalities. And why do I say geometry? Well, if we think about the shape of the constraints, right? So again, linear programming.
We can't see your board.
You can't see my board. Did my screen share
Also,
stop
you're
working?
echoing.
How odd. Okay, let me futz around a little bit more. Hang on a minute. Why would I be echoing? What do you see instead of my board?
The picture of you. That's
Okay.
The picture with no video.
Somehow screen share stopped working. Okay, let's try and fix that. Okay, do we see the board?
no.
No. All right. Nope, that's not it. Oh, I know what I need. Okay. Now we should be okay on the audio. Yes?
Yeah.
Yes.
Yeah.
Yeah.
Now we have to get the screen share back. How did I lose it? Good. All right, and now back to the board. Okay. Good. All right, so now we're going to talk about the geometry of systems of linear inequalities. And linear programming in general is working in n dimensions, but I don't have an n-dimensional Blackboard, so we're going to be using a lot of pictures of the two-dimensional version. So if I think about a 2D linear programming problem, each of my constraints is a half space. It's a line, right? It's a line which allows the points to be on one side of that line. And so if I take a whole bunch of constraints, they tend to define some polygon in my two-dimensional space, right? And this generalizes to n dimensions. The set of constraints ax less than or equal or greater than or equal to b, or less than or equal to b, whichever I prefer, is an intersection of finitely many half spaces. In however many dimensions. And that is called a polytope. Okay. And for those of you who've done some geometry, it is a convex polytope. Okay. If x is in the polytope and y is in the polytope, then any point which is a combination of those 2 points is also. That is, if you take any 2 points in the polytope and you draw the line between them, the line stays inside of the polytope. And the reason for this is, again, that the polytope is an intersection of half spaces, right? It's pretty easy to prove that if 2 points are on one side of a line, then the segment between them is also on the same side of the line. And so the segment is on the same side of every line, and therefore the segment is entirely inside of the polytope. Okay. Now, if we look at this polytope and talk about the linear program that it defines, we can also look at the objective function, right, which will point in some direction. Let's call that C, right? And let's suppose that my goal is to, let me make it less ambiguous. Let's suppose that my goal is to maximize C, X. Okay. Where am I going to find the optimum solution in this polytope that I've drawn?
Corner.
Exactly. So the claim, which right now is just an intuition, is that the optimum solution is generally found in a corner of the polytope. And so what we're going to be doing for much of today is just defining what a corner is, right? But why is it that we would expect that the optimum can be found in a corner?
I mean, you can imagine starting from an initial guess, traveling along the gradient direction until you hit a constraint. So you'd like hit a face, and then now traveling along the face until you hit another constraint, yada, yada, yada.
Very good. So let's think about that, right? So the obvious thing to do is to start somewhere in the polytope and then move in the direction that improves the objective function, right? And I'll keep moving until I hit some constraint of the polytope, okay? Is this going to be the optimum? Well, not necessarily. Hitting this constraint stops me from moving in my original direction, but there still appear to be a direction in which I can move that improves further on the value of my objective function, right? And so I'm going to be able to keep moving until I hit some other constraint, right? And at this point in my picture, right, I've now got two constraints that are each preventing me from improving on my objective. And those two constraints together mean that I can't get any better in any direction. So we need to define these corners, and we're actually going to look at a pair of definitions of corner. So a vertex is a point that is not a convex combination of two other points in, or of any other points in the polytope, okay? So, you know, the points on this line are not vertices. And what that means is that they're not at the edge of, they're not at the corners of the polytope. You can, from anywhere on this line segment, you can basically move in any direction and still be in the polytope, okay? And if moving in any direction keeps you in the polytope, then for any objective function, there's a direction you can move in that improves it, okay? And that means that you're not going to find your optima in these points that are convex combinations of other points. We're also going to talk about extreme points. Okay. An extreme point is a point that is a unique optimum solution for some objective function C. And my claim is that these two concepts each capture where the optimum points can be in a polytope. And in fact, we're going to show that they're equivalent. Okay. So I'm going to start by talking a little bit more about vertices. Sorry, I'm going to start by talking about yet another characterization of optima. In order to do that, I need to talk about a basic solution. So I'm going to define a constraint to be tight. Okay, if I have a constraint ax less than or equal to b, or ax equals b, or ax greater than or equal to b, is tight when ax equals b. Okay, so you'll notice that equality constraints are always tight, but inequality constraints are tight only when ax has the particular value equal to the constraint. Okay. Now, for an n-dimensional linear program, we say that a particular point in the program is basic if, first of all the equality constraints are tight, which happens automatically if the point is feasible. And second, n linearly independent inequality constraints are tight. Okay. So again, looking at my polytope over here, this point that serves as the optimum is the intersection of two linearly independent constraints. And this point, which we think could be an optimum for this value, for this objective function, is in fact the intersection of these two linearly independent constraints. Yes?
Shouldn't it be n minus m linearly independent inequalities? N, the number of variables minus the number of equalities.
No, because right now we're looking in the form of we're looking at a polytope formed by ax greater than or equal to b, or ax less than or equal to b, right?
But then the first, what is the point of the first all equality constraint?
Oh, well, so some of the, that's a fair question. If we're only looking at ax greater than or equal to b, we won't have this constraint. We won't have any equality constraints, but this definition holds. Oh, I see what your question is. Right. So you're right. Here's what I wrote incorrectly. It's not inequalities that have to be tight. It's n linearly independent constraints that need to be tight.
I see, thanks.
Okay. So yes, so in other words, you have these n constraints that are tight and they have to include all of the equality constraints and however many other inequalities are needed in order to bring you up to n. Okay. And if this point, if this basic solution is feasible, then it's called a basic feasible solution. So now we have sort of three different notions of where we're going to find optima. Okay, there are these corners which sort of stick out and are therefore not convex combinations of other points in the polytope. There are these extreme points that are just as far as you can go in some direction. And then there are these basic feasible solutions and linearly independent constraints. Okay. And these are all kind of characteristics of the optimum. And in fact, they're all the same. So we can prove that any vertex is an extreme point and is a basic feasible solution. And I'm not going to prove this full out, but I'll give you some pieces of the proof. Okay. And I'll let you fill in the others if you care. I mean, this is math, not computer science, so I don't want to spend too long on it. But here are some pieces of the proof. So first of all, let me prove what seems like a separate lemma, but will actually tie back to this claim. The lemma is that any standard form LP which is the ones that are written as AX equals B and X greater than or equal to 0, that has an optimum, has one at a basic feasible solution. Okay. So first step towards understanding optima is to say that when there is one, it's at a basic feasible solution. Okay. So let's think how to prove this. Okay. So we're supposing there exists an opt, but if it is at a basic feasible solution, then we're done. So suppose that we have an optimum that is not at a basic feasible solution. How can we make progress towards what this lemma claims? Well, if it's not at a basic feasible solution, it implies that there are less than n tight constraints. On this point X, right? So this means that there is a degree of freedom to move X while keeping these tight constraints. Right? Each of the tight constraints is a hyperplane in our vector space, right? Each of these tight constraints has the form AIX equals BI, right? I have less than n of them. So if I take the intersection of less than n tight constraints, AIX equals BI, what do I get? Right, so coming back to our two-dimensional case, right? A single constraint, AIX, this is why I didn't go into computational geometry. I can't draw. A single constraint of the form AIX equals BI is just a line, right? It's a subspace of the entire space. If I take an intersection of two constraints, it gives me a point. Similarly, in higher dimensions, right, the intersection of n hyperplanes gives me a point. But I have, oh, thank you so much. I wouldn't call them beautiful, but they're very personal. So if I have an intersection of n constraints, I get a unique point. But if I have an intersection of less than n constraints, then I get a subspace of the original space, right? But a subspace has degrees of freedom, right? I can move in the subspace defined by these tight constraints. Now, if I move, what happens to the objective? Well, there's three possibilities. Right? It can improve the objective, worsen it, or leave it unchanged. So let's consider these three cases, okay? What would it mean if moving in this subspace improved my objective function?
There was another optimum that or there's another solution that's higher than the optimum.
Right. If I can improve, that would mean that my current position is not optimum, contradicting my starting assumption. Okay. Now, what if moving in a certain direction makes things worse?
We move in the opposite direction?
Exactly. Moving opposite this direction improves, which takes us right back to the assertion that we're not at the optimum. So really the only possibility, given our assumptions, is that moving in the subspace leaves the objective function unchanged. Okay. So now let's home in, and so that means the entire subspace is optimum. Right? Now, in a general polytope, it is possible to have an entirely optimum subspace and no optimum at a basic feasible solution. But now it's where I'm going to use the fact that we're in standard form. And this is why practitioners like standard form. Okay, theoreticians like canonical form because it's very pretty, but practitioners like standard form because of this fact, which makes it useful. Okay. My subspace contains a line, right? Because that's just a smaller subspace. Okay. Through my current X. And I'm going to write it as X plus epsilon D. Okay. For some direction D. And I've already argued that all the points on this line are optimal. Okay. Now, in one direction of this line, some coordinate xi is decreasing. Okay. But remember that the standard form has this constraint that all the x's should be greater than or equal to 0. So I'm going to keep moving in this direction until some xi hits 0. Okay. So what does it mean that some xi has hit 0 that was not previously 0?
We made another tight constraint.
Exactly. We now have a new tight constraint. Okay. So if I am at an optimum and it is not a basic feasible solution, I can move to make a new tight constraint. Okay. So now just repeat until, well, until what? Until my assumptions no longer hold, right? I started by assuming I was not at a BFS. I'm just going to repeat this until there are n tight constraints, i.e., I am at a basic feasible solution. Okay. So this completes the proof that if there is an optimum, there is an optimum that is at the intersection of n-type constraints of the polytope in standard form. Now I asserted, and now let me show you, that in canonical form, you might not have the optimum at a basic feasible solution. And I can demonstrate that for you. If we just consider the optimization function, or the canonical form LP that says to maximize X, subject to the constraint that X is less than or equal to 1. Okay, so if I think about this as a two-dimensional linear program, okay, so there are two variables, X and Y, although I'm not actually mentioning Y at all in my LP. Okay, but the constraint that X is less than or equal to 1 says you can't go past this line. And so the maximization function will simply run into this line and get stuck. And you see that there's no basic feasible solution because there's only one constraint. There is no intersection of two constraints, right? So this is kind of the problem with the canonical form, is that you can have these unbounded polytopes, which nevertheless have optima. In standard form, these constraints that all the x's be greater than or equal to 0, okay, you've seen how well I do in 2 dimensions. Let's try the 3-dimensional version of this. My constraint that ax equals b tends to look like some sort of simplex that is constrained by the positive, to be in the positive orthant. And so it can't stretch on forever. And so if you get to the optimum, you won't be able to go indefinitely in any direction. And so you'll always eventually collide with one of the corners of this shape. And as I said, that is why standard form is preferred by practitioners, because they can assume that there always is a basic feasible solution. Okay. Now we've actually proven something a little bit stronger, which is that if there exists an x of a given value in standard form, then there exists a basic feasible solution that is no worse than that value. Okay, the adjustment process that we did is basically an adjustment process that does not make your objective function worse. Okay, and that's useful for a variety of algorithms that we're going to be talking about later. Okay. Okay, so that's given us our first look at optima, which is that we have this notion of a basic feasible solution, an intersection of n constraints, which defines where the optimum is. Starting next time, I'll relate it to these other two forms, the vertex and the extreme point. And then we will start talking about algorithms for verifying and then constructing the optima of linear programs. So I will see you on Wednesday. I'm also going to post a form asking for feedback on this lecture format. Let's ignore the time spent figuring out how to get the pencil to listen. I'd love your feedback on whether this works better or worse than the whiteboards and camera. So look for that form later on today. Okay. And hopefully you saw the announcement about very late office hours that we're starting today for people who are coming in from remote time zones. Any final questions?
I have a question about the previous lecture.
Yes.
So in the mean cost flow algorithm, in the scaling algorithm, that when we scale one bit, you mentioned that so we have these deficits and excesses that we send flow from excess to deficit and then send it back via solving another mean cost flow problem.
Yes.
So the way I see it is like we basically don't change the flow value, but just find some circulation that
Exactly.
makes the cost minimum for that amount of flow.
Well, it's not changing the flow, right? It's
Right.
it's
For
just
that
changing
amount
the
of flow,
cost.
it minimizes the cost.
Yes.
But then shouldn't we add some, we might be able to add some flow because of the increase in the capacities.
Well, we're not increasing the capacities, right? So if you think about it, if you send flow along a circulation, it doesn't actually add capacity to any cut.
I mean, when we shift a bit, we increase some of the capacities by 1, right?
That's correct.
And then we find some circulations to make that flow mean cost. But then my question is, maybe we can be able to like add more flow to that because of the
Right. So there's two separate pieces to this scaling algorithm for min cost flow, right? There's keeping the edge weights positive, and there is using up extra capacity.
Right.
These are two separate pieces, right? So when we scale in a bit, we create some extra capacity, some of which might be on negative edge weights.
Right.
So what we do is we use the excesses and deficits approach to clear out the negative weights to create new feasible prices, right? Once we have cleared out the negative weights, we use shortest augmenting paths in order to send the remaining flow.
Okay.
But we already know that shortest augmenting paths does not create negative weights.
Right. So because in the lecture video, I think you didn't mention the second part. I thought it's.
I see.
I understood.
Yes. So we need these two separate steps. We need to clear out negative costs.
I see.
But you'll notice that in both cases, we use shortest augmenting paths, right? We saturate the negative weights. We use shortest augmenting paths to clear them out. This gives us new feasible prices. Then we use shortest augmenting paths to use up the remaining capacity.
Right. Got it.
Okay?
Thanks.
Sure. Any other questions? All right, then I'll see you on Wednesday.